Hi, folks. My name is Kelly Holly Bockelman, and it is my distinct honor today to introduce Dr. Sarah Burke Spolaor. Sarah is an assistant professor at West Virginia University, and there she studies the evolution of supermassive black holes and is one of the world's experts on gravitational wave astronomy with pulsar timing. She also studies studies of radio transient phenomenon. Today she's going to be talking about massive black holes on the move. Sarah, I'll give you a 4-minute warning for the whole session, so take it away.
Thank you. And just to check, you could share my screen, or you could see my shared screen?
Yep.
Okay, so this will by necessity be brief, but I'm going to highlight primarily actually recent multi-messenger science at low gravitational wave frequencies, and try to give you a bit of context just to see the discussion later. And in 5 minutes, I'll ask you to participate to combat Zoom fatigue. So be ready to put something in the chat. All right, so our story starts deep within a merger remnant, and back in that merger remnant, two giant galaxies have merged, and kaboom, there's a giant supermassive black hole binary down at the center. These are big whopping, gas-sucking events. Gas is being funneled onto these objects potentially by that merger that's ongoing around them. And this is really potentially makes them really excellent multi-messenger objects to look at as active galactic nuclei with some sort of oddball observational properties. As I said, though, I'm going to focus a little bit more on the gravitational wave side of this. And of course, multi-messenger science requires that non-electromagnetic messenger. And most of my focus today will be on what pulsar timing arrays have been doing. But of course, LISA and pulsar timing arrays will both be the real powerhouses for massive black hole exploration, particularly for these binary populations. However, I wanted to point out that these two techniques are very much complementary, with different populations probed, at least slightly different, and slightly different astrophysics that are able to be probed by each. And here I'm just showing some graphics comparing LIGO, LISA, and pulsar timing arrays and the timescales over which they're able to see binary black holes. Of course, LISA and pulsar timing arrays are much lower frequency, therefore much longer orbital periods. We expect LISA to be launching in something like 2030 and start detecting events soon after that. Pulsar timing arrays have been running for something like 20 years now, and in a concerted effort for something like 10 years. And we really expect our first discovery of the gravitational wave background in the next couple of years. Here's a plot that was from a recent review I wrote on pulsar timing array science. And this is just to show the complementarity in terms of mass scale for these various experiments. You can see that LISA is really probing out to high redshift at these lower masses. And of course, at those high redshifts, you really expect the lower masses to be dominating. You can see that nanograv and International Pulsar Timing Array, that IPTA, it goes out to very high redshift potentially, but we don't really expect that many supermassive black holes to be occurring at redshift of even 10 to 100, at least not in binary systems. However, these techniques are both complementary in mass range and also in orbital timescale and just timescale of movement of these black holes. Now, I wanted to divide here two types of multi-messenger science that can be done with supermassive black holes. And this is based on the types of signals that gravitational wave detectors will see. And on the left here, I have what we would call, or most of us would probably consider, the traditional individual system type of multi-messenger science. And LISA and pulsar timing arrays will explore these most massive systems while they're still potentially influenced by the galaxy's environment. So we get to probe that interplay. Pulsar timing arrays preferentially will be discovering binary black hole systems in much earlier inspiral, so relatively stable orbits. Post-Newtonian effects aren't really dominating. And potentially these two could be, two supermassive black holes could be hosting active galactic nuclei. We expect the detection of these individualized systems in the next few years, we believe, based on predictions. Most predictions expect us to find something like 2 to 10 detections by 2030. And that very much depends on the evolution of the universe and constraints that are still open in the evolution of the universe. On the other hand, LISA will track really the final few hours to perhaps the final few weeks of inspiral and that actual coalescence event where they actually slam together and some of the ring down. So this will be preferentially probing the actual physics of the black holes, gravity and spin, and even mass evolution as a function of redshift. Because they have that actual chirp signal with that inspiral, you're able to get a nice standard siren out of these objects. So this is not to say that pulsar timing arrays won't necessarily do that, but it's much less likely because the number of binary supermassive black holes at that mass range that will be occurring for us to see is relatively small. So I wanted to do a little bit of time highlighting today what some might call non-traditional multi-messenger science, and this is multi-messenger astrophysics of the gravitational wave background. So the stochastic background is the ensemble signal from all of the binary supermassive black holes in the universe. Pulsar timing arrays will detect this, and we expect it to be our first signal that we will detect, possibly in the next 2 to 3 years, maybe this year, who knows. But we're working very hard to detect this signal. And I wanted to highlight some really excellent work that's been done recently by pulsar timing arrays to actually use limits on this ensemble signal that we've had so far in concert with electromagnetic data to do some really neat creative things. And just to understand, to help you understand how we access this science, it's worth knowing how we actually determine what a gravitational wave background should look like. It involves multiple ingredients, the main constituents of which are redshift dependent merger rates. So we have to know what the redshift dependence of those, the source galaxies are for these binary supermassive black holes. Going into those estimations are many parameters that are probed by electromagnetic studies. For instance, the galaxy mass fraction, the galaxy merger rate, merger mass ratios, and looking at things like merger and binary inspiral timescales. So these are all parameters that can be probed by electromagnetic observations, and they have been. Many of them have been constrained by this to better or to worse precision as a function of redshift. The other thing that we need to do is say, if we know a little bit about what the galaxies are like, we want to know really for pulsar timing array gravitational wave signals and for LISA gravitational wave signals, how massive the binary itself is, the black hole binary. So we can cast those merger rates and the masses of those mergers and the mass ratios of those mergers into actual mass ratios of supermassive black holes by using host black hole relations. So for instance, the famed bulge mass black hole relation that I'm showing here, and there's also the relationship between the massive black hole's mass and the velocity dispersion. So putting these two ingredients together, we can get a predicted massive black hole pair population. So we can do this in a number of ways to actually predict the gravitational wave background, but with a limit from pulsar timing arrays on the gravitational wave background, with a limit particularly that's strong enough, we're able to constrain some of the less constrained pieces of science in this list of yellow ingredients. So I wanted to highlight particularly 2 areas of study. One of them is that we have been looking at constraining candidate binary populations with pulsar timing array limits on the gravitational wave background. And the idea behind this is that from a large population of suspected binaries, and this is what I'm showing here, is there was a stipulation that many blazars are periodic, and this was based on observation of a number of blazars showing year to a couple of year periodicities. It was hypothesized that perhaps many blazars are actually binary supermassive black holes. Now you can take that population of blazars and say we know what mass they are and do a luminosity function for them and try to anticipate what the gravitational wave background should look like if all blazars were binary supermassive black holes. So this was a great study by Miguel Holgado. And what I'm showing here in the plot is a figure from his paper. And on the left panel, you see, this is just the probability distribution as a function of the strength of that gravitational wave background. And that's at just some fiducial period of 1 year. Well, sorry, 1 over 1 year is the frequency. So you can see that if you estimate that something like 10% of this population is a binary with something like less than 5-year orbits, those are the periodicities over which have been discovered, you can compare these with the pulsar timing array limits from various pulsar timing arrays around the world. This is the Parkes pulsar timing array, European pulsar timing array, and Nanograv, which is the North American contingent. And you can see that, in fact, these pulsar timing arrays put much better constraints than even 10%. So on the right, I'm showing the actual constraint these pulsar timing array limits imply. And the inferred statement that came out of this was that really no more than one blazar in 1,000 can host a supermassive black hole binary with period of less than 5 years. That's the orbital period. So another really big area of pulsar timing array science that we've been pursuing so far with multi-messenger components is actually looking at the limits that we can set based on those ingredients that I showed before. So on the left, I'm showing, again, a couple of different measurements that have gone into this massive black hole bulge mass relation for supermassive black holes and their hosts. And we were able to take, my collaborator, Joseph Simon, and myself were able to take the limits from past pulsar timing array experiments and say, if we make a universe full of supermassive black hole binaries based on these relations, basically we are not, we are showing that we are not having the black holes that are as massive as these two measurements have shown them to be. So we have limits that actually demonstrate that these host black hole relations are a little bit too over predictive for the masses, at least at the very large mass scales. This is not to say they're entirely wrong in their measurements, and we don't expect that they're wrong in their measurements, but there have been a number of papers showing that there may be biases in the way that we measure supermassive black hole masses in these electromagnetic observations of supermassive black hole masses. So that may be biasing these relationships that have been empirically measured, biasing them upwards. On the right, I'm showing an analysis that was done with Nanograv, the North American Pulsar Timing Array, with their 11-year data set, which is the most recent data set. And here I'm showing how we are able to put constraints on both the stellar core density and the eccentricity of binary systems in the core. And this is based statistically on the average stellar density of galaxy cores and the average eccentricity at which binaries enter, well, two black holes enter their binary state. This also depends, it's covariant with the black hole mass relations, but we're able to actually probe these detailed physics of astrophysics of the galaxy cores and the dynamics in these host galaxies. Now, this is not to say that we don't actually do continuous wave science. This is a really big focus of our work. So we don't just work on doing multi-messenger science with gravitational wave backgrounds. This is a short talk, so I don't have a ton of time to do these other ones, but I wanted to just highlight that we've done a number of studies, and just 5 of them are highlighted here. We're able to make statements like our pulsar timing array horizon, the deepest horizon is something like 120 megaparsecs, and it's growing every year. You know, every moment we take another data point.
Yeah, got 3 minutes.
Okay, thank you. We know that there are no 10 to the 9 solar mass black holes or larger black hole binaries in Virgo cluster. We've actually shown that knowing the period of a binary supermassive black hole as measured by an electromagnetic experiment can significantly raise gravitational wave search sensitivity. And this is by a factor of something like 10. So my student, Caitlin Witt, led a recent paper on that that's now on archive. We can also put meaningful limits on the mass ratios of any potential binary in hundreds of nearby galaxies. And we are now searching for both eccentric and circular sources. This was computationally previously infeasible, but now we've gotten new techniques to actually run those searches. So I wanted you to really quickly post in the chat. I'll give you 30 seconds for this. I'd like you to throw in an idea for identifying a binary or coalescing massive black hole with light. So let's see what kind of chat things come in here. There's got to be some experts here. Radio flare, yeah, that's a good one. So you might even get something like a tidal disruption flare, greater number of tidal disruption flares from a supermassive black hole binary system. Accretion disk lensing signal, that's right, you could have binaries passing by each other and getting some lensing, runaway stars. Yeah, runaway stars are a little bit hard to detect because you know, you're studying these galaxies that are quite far away, but maybe you know more about it than I do. Alexi, thank you. Modulation of AGN luminosity is a really big field right now that's been studied. So I think you guys can all see that these comments that are coming in. The point I wanted to make, because I didn't have time to cover them all, is that there are tons and tons of multi-wavelength signatures that we expect. So yeah, X-ray periodicities, even modulations in radio jets from a secondary black hole. so many signatures that we expect for even a very close binary supermassive black hole. But all of these are really hinging on the idea that we need to know something about when AGN and broadline regions and any of those illuminative signatures are actually disrupted by that binary system. And is there a point where that binary decouples from the surrounding gas that then it would no longer operate in conjunction with that surrounding gas, therefore put out no electromagnetic signal? That might be a thing. If we might actually decouple, and then after that point, not actually see any more electromagnetic signatures. We are pretty confident that at pulsar timing array scales, where these binaries are very far apart and quite stable, there's not enough gravitational interaction to get rid of all the electromagnetic signatures. I know there's some debate at LISA scales, and even after the merger, whether and what time scale over which a signal might occur, but all bets are out, but most are positive. So the last thing I wanted to do was just see the discussion session. And I wanted to mention that, I didn't talk much about coordination between multi-messenger facilities, but perhaps this could be a focus of the discussion session. And depending on who shows up, perhaps we could talk about one thing that I think hasn't gotten much attention, which is what will new surveys actually constrain about galaxy evolution that will allow pulsar timing arrays to dig a little bit deeper into individual parameters like, massive black hole host relations or merger timescales that we are a little bit better at doing than electromagnetic observations. I'm also curious to hear from observatory representatives about organic binary discovery, what kind of signatures might come out. We've got a lot of thinking about that. And also strategies in just identifying pulsar timing array and LISA source hosts. And I'm showing here on the bottom a nice study that was done by Jana Goldstein showing for the International Pulsar Timing Array, or IPTA-like array, how well we can localize with pulsar timing arrays. It's not that great. It's something like a couple of 100 square degrees. We know a little bit about the source populations, so we think that probably nearby sources will be more likely to be detected, and the most massive ones, so that can give us a cut and give us something like 500 galaxies in our 90% confidence region. So perhaps we'll then go to catalogs and do some kind of cut, maybe based on LSST light curves, and then go on to do targeted surveys of some large number of galaxies. So thanks for listening. I just wanted to mention that for greater detail of any of these topics, there are 2 reviews that came out recently. At least the first one is really excellent, and I like the second one too. Thank you.
Thank you very much, Sarah. Unfortunately, we have no time for questions, but we have recorded some great questions in Q&A, and we can you can stay after and answer some of them. Thanks.
Yeah, glad to.